Welcome to GE Fun Facts Online. Today, we are diving into the deep end of theoretical physics to explore a geometric object that is currently rewriting our understanding of reality. We are looking at the Associahedron. If you follow popular science, you might have heard that phrase, or perhaps its cousin, the Amplituhedron, thrown around in headlines about the death of spacetime. But today, we are going to move past the headlines. We are going to look at the mechanical problem in physics that necessitated this discovery, the specific geometry of this object, and why it suggests that space and time are not the stage the universe plays out on, but rather a hologram projected from a deeper, timeless structure. Let's begin with the status quo. The Standard Model of particle physics is the most successful theory in human history. It predicts the magnetic moment of the electron and the behavior of the subatomic world with staggering precision. However, for the physicists working in the trenches, this success comes at a surprisingly steep price. It is a computational nightmare. To calculate how particles interact, how they smash together in a collider and scatter, physicists have relied for decades on Feynman diagrams. We have all seen these, those little doodles of squiggly lines and arrows. They look simple, but they are rigorous accounting tools. Each line and vertex in a diagram represents a mathematical expression. To find the probability of a specific scattering event, you have to draw every possible way that interaction could happen, translate those drawings into math, and sum them all up. For simple events, this is fine. But as you demand higher precision, or as you look at more complex interactions involving more particles, the number of required diagrams explodes. It goes from a few dozen to thousands, then to millions. A calculation that might fit on a napkin for a rough estimate grows into an equation that would literally fill a library. This complexity is the first clue that something is wrong. It suggests a massive redundancy in our method. It implies that tracking particles as they move through space and time is an incredibly inefficient way to describe the universe. This is known as the Feynman bottleneck. To understand the solution, we have to understand the problem with Feynman diagrams. Richard Feynman's method is built on two sacred pillars of physics: locality and unitarity. Locality is the rule that particles can only interact when they meet at the exact same point in space and time. There is no spooky action at a distance. Unitarity is the rule that probabilities must add up to 100%. Particles do not just vanish from existence. To preserve these two rules, Feynman diagrams force physicists to account for every conceivable way an interaction could happen in spacetime, including the creation of virtual particles, ghostly entities that pop in and out of existence during the interaction, never to be observed directly. The resulting math is a Rube Goldberg machine. You end up with thousands of terms, huge algebraic monstrosities. But here is the smoking gun. When you finally do the calculation, when you sum up those millions of diagrams, the terms often cancel each other out. The pluses kill the minuses, the complexity collapses, and you are left with a surprisingly simple, elegant answer, often just a single term. This cancellation tells us that the complexity was not a feature of the universe. It was a feature of our bad translation. We were describing a simple truth using a complicated language. This is where the work of visionary physicists like Nima Arkani-Hamed and his collaborators comes in. They asked a radical question: is there a way to get the final answer directly, without forcing the physics to obey space-time rules step by step? Is there a way to bypass the virtual particles and the redundant algebra? The answer lies in geometry. The breakthrough came when researchers stopped asking how particles move through time and started asking about the shape of their interaction probabilities. They discovered that if you move into an abstract mathematical domain known as kinematic space, a space defined not by where particles are, but by their momenta and energies, the scattering amplitudes correspond exactly to the volume of a geometric object. For a specific class of scalar particle interactions, known as bi-adjoint phi-cubed theory, this object is the Associahedron. So what is an Associahedron? It sounds like a sci-fi artifact, but it is a very specific shape discovered in the 1960s by Jim Stasheff, originally for the study of homotopy theory, which deals with continuous deformations in mathematics. It was not invented for physics at all, which makes its appearance here even more spooky. To visualize it, do not try to picture a 4D hypercube immediately. Start with a polygon. Imagine a hexagon. Now ask yourself a combinatorial question. How many ways can you cut this hexagon into triangles using non-crossing lines connecting the corners? This is called triangulation. Each distinct way you can triangulate the hexagon corresponds to a single vertex or corner point of the Associahedron. If you can transform one triangulation into another by flipping just one internal line, those two vertices are connected by an edge. When you map out all possible triangulations of a hexagon and their connections, you build a three-dimensional shape with 9 faces and 14 vertices. That is the 3D Associahedron. If you add more particles to the interaction, the polygon you are triangulating gets more sides, and the resulting Associahedron blossoms into a higher dimensional hyperpolytope. The magic is this. The physics of particle scattering mimics this exact combinatorial dance. When particles scatter, the different channels through which they can interact map perfectly onto the triangulations of a polygon. The Associahedron creates a dictionary between the abstract math of triangulations and the physical reality of subatomic collisions. In the old Feynman method, you sum thousands of diagrams. In this new geometric method, you simply calculate the volume of this single polytope. And here is the kicker, the locality and unitarity that Feynman diagrams work so hard to preserve. In this new picture, they are not inputs, they are outputs. They appear naturally as properties of the geometry itself. Locality is just the way the facets of the jewel fit together. Unitarity is the fact that the jewel is a closed loop. You don't have to force the universe to make sense. The geometry forces it for you. Now we need to clarify a point of confusion that often arises in this topic: the difference between the Associahedron and the Amplituhedron. You might have seen the Amplituhedron making headlines back around 2013. It is crucial to understand the relationship between these two jewels. The Amplituhedron is the more famous cousin. It was discovered first in this context, and it is designed for a highly symmetric theory called planar n equals 4 supersymmetric Yang mills. That is a mouthful, but think of it as a toy model of our universe, a maximal perfect version of particle physics that includes supersymmetry. The Amplituhedron showed that scattering amplitudes in this perfect universe are volumes of a shape generalizing a polygon into a geometric space called the Grassmannian. But critics argued that this was just a fluke of the toy model, that it only worked because the theory was so symmetric and perfect. The Associahedron is the rebuttal to that criticism. It represents the next step in the revolution. While the Amplituhedron works for the supersymmetric toy universe, the Associahedron applies to a simpler, non-supersymmetric scalar theory. It proved that this geometric magic wasn't just a lucky break. It hinted that all quantum field theories, perhaps even the messy, complex Standard Model that describes our real universe, have their own corresponding jewels. The Associahedron acts as the primitive skeleton of these geometries. It captures the bare-bones structure of how things combine, that is, associativity, revealing that the algebraic structure of particle physics is identical to the geometric structure of these polytopes. This brings us to the most mind-bending implication of this research, and the part that changes how we view reality: the death of spacetime. For centuries, physics has assumed that space and time are the containers of reality. We assume things happen in space over time. It is the background grid. But the Associahedron suggests that spacetime is not the container, it is a hologram. In this new view, the fundamental reality is the geometry itself, the positive geometry of the Associahedron, living in that abstract kinematic space. The physics we observe, Particles moving, banging into each other, obeying cause and effect, is just the shadow this geometry casts. When Naima Arkani Hamed says spacetime is doomed, he does not mean the universe will implode. He means the concept of spacetime has reached its limits as a fundamental description. Just as the smooth surface of water is actually made of discrete water molecules, the smooth continuum of spacetime is likely an emergent approximation of this deeper, discrete geometric structure. This actually helps resolve one of the biggest tensions in physics. We know that quantum mechanics, the math of the small, and general relativity, the math of gravity and spacetime, hate each other. They mathematically break down when you try to combine them at the singularity of a black hole or the Big Bang. But if spacetime is not fundamental, if it emerges from something else, like the Associahedron, then the conflict might be an illusion. We have been trying to marry two shadows, when we should have been looking at the object casting them. This has launched a new program in physics, often called surfaceology. It is a hunt for the specific shapes that correspond to the real-world particles, quarks, gluons, and electrons. Researchers are finding generalized associahedra and cluster polytopes that extend these ideas to more complex interactions. They are finding that the singularity structure of these shapes, the way their faces and edges meet, predicts physical phenomena like soft limits and factorization, which were previously derived through laborious calculus. We are witnessing a shift in the language of the universe. We are moving from the calculus of motion to the combinatorics of shape. The Associahedron proves that the complexity of the quantum world is a disguise. Underneath the chaos of infinite Feynman diagrams lies a crystalline order. The universe, at its most fundamental level, may not be a churning machine of temporal evolution, but a perfect, static diamond, whose facets tell the story of everything that happens, all at once. The math is no longer about calculating the next second. It is about exploring the geometry of the eternal now. That is the Associahedron. It is efficient, it is beautiful, and it might just be the true face of reality.